Listen, there's a war going on down there. The quiet war. The never-ending battle between metal and corrosion. This quiet war is fought on many fronts. From the scheduled day-to-day corrosion inspections and phase maintenance inspections done here at the local squadron level, to the in-service repair evolutions done here at the Naval Air Rework Facility. This two-part program is designed to help you win the quiet war by familiarizing you with the fundamentals for identifying and treating corrosion.
Approximately 1,500 man-hours of each P3 processed here is completely orientated towards corrosion removal and correction. Preventative maintenance at the squadron level is the key to corrosion prevention. 5 minutes of corrosion preventative maintenance at the squadron level can prevent 5 hours of corrosion processing here at the NARF. The sailors are the key to corrosion prevention. 75% of the corrosion rework done here could be prevented at the squadron level. 75% represents approximately $100,000 per aircraft cost to the customer that could be prevented and utilized elsewhere in their maintenance program or increase the number of aircraft brought into the NARF for rework.
Think about that. 75% of the corrosion work done here at NARF could be prevented by consistent, reliable corrosion control practices here at the local squadron level. In order for any local corrosion control program to be effective, aircraft must be cleaned, inspected, lubricated, and, if necessary, treated for corrosion on a regular basis. Part 1 of this program will define the various corrosion types you are most likely to encounter, explain their causes, and identify the areas and components of the aircraft where they are most likely to be found. The most common type of corrosion is direct surface attack, or surface corrosion. Surface corrosion is most commonly caused by exposure of the aircraft's unprotected bare metal surfaces to water, salt spray, and other natural or man-made contaminants. It can attack nearly every unpainted metallic surface of the aircraft, inside and out. Surface corrosion is a never-ending threat that must be fought constantly. Another type of corrosion common to P3 aircraft is galvanic corrosion, also known as dissimilar metal corrosion. Aircraft components often contain 2 or more dissimilar metals in contact with one another. If such a point of contact between dissimilar metals is contaminated by dust, dirt, salt, or any other substance that is soluble in water, galvanic corrosion will occur. Galvanic corrosion occurs if condensation, sea spray, rain, or any other form of moisture is also present. Galvanic corrosion can occur whenever 2 dissimilar metals come in contact with one another. Areas that are particularly prone to galvanic corrosion include steel rivets in aluminum aircraft skin, as you see here, antenna mounting points, steel hinge pins in aluminum hinges, as in these drop-down panels, and the steel fasteners in the windshield frame. Remember, Adjacent dissimilar metals, contaminants, and moisture combine to form galvanic or dissimilar metals corrosion. Pitting is another type of corrosion that is common to P-3 aircraft. The surface cavities characteristic of pitting corrosion vary in depth from shallow depressions to deep pits of small diameter. Pitting, which is galvanic in nature, is the result of physical and/or chemical variations in the composition of metals exposed to corrosive environments. In its early stages, pitting may not be so apparent because the pits may be filled with corrosion product, appearing as a gray-white powder on aluminum, red rust on steel, or a blue-green powder on copper. Areas on the P-3 where pitting corrosion is likely to occur include high heat areas, such as the APU exhaust, and any bare aluminum surface. Now let's consider two types of corrosion, which have similar characteristics: intergranular corrosion and exfoliation corrosion. These are the two most dangerous types of corrosion. They differ from all other types of corrosion inasmuch as the damage they cause begins inside the metal, where it is unseen, causing serious damage before it is detected. Recognition of intergranular and exfoliation corrosion is vital. Undetected and untreated, it can cause serious structural damage to the aircraft. Intergranular corrosion occurs most often in metal alloys, which undergo heat treatment and cooling processes during manufacturing. It also occurs in other metals that have been heat treated to increase their strength, and in metals that have been subjected to localized overheating from welding or from fire damage. Because it starts inside the metal, intergranular corrosion can often exist with no visible external signs. Looking at the metal surface, you might only see a pitting type of attack, or as in this case, a bulge in the metal surface. If you suspect intergranular corrosion, consult the Structural Repair Manual, NAVAIR 01-75-PAA-3-1, to find the damage limits and determine the level of maintenance required. Exfoliation corrosion is an advanced form of intergranular corrosion. The visible signs of exfoliation corrosion include peeling, flaking, layering, or scaling metal surfaces. Areas on the P-3 where intergranular and/or exfoliation corrosion is likely to occur include wing planking surfaces, wing mooring points, the horizontal and vertical stabilizers, and the aluminum angle attached to the wing spar cap and firewall inside the number 1 and number 4 engine nacelle. Crevice attack corrosion, also known as concentration cell corrosion, is yet another type of corrosion that threatens P-3 aircraft. Crevice attack, or concentration cell corrosion, thrives in voids, crevices, flanges, bilges, and other water traps that are often hard to reach and hard to clean. Periodic plane washdowns are fundamental to successful corrosion control. However, if drain holes are obstructed and cleaning compounds and wash water are allowed to collect and remain in crevices and other water traps, crevice attack or concentration cell corrosion will result. Areas that are particularly vulnerable to this type of corrosion include the wing flap wells, the fillet panels on the horizontal stabilizer, and any bilge area in the aircraft where water and other contaminants are likely to collect. Fretting corrosion is next on our list of corrosion types threatening the P-3 aircraft. Fretting corrosion develops when two heavy surfaces that are in contact with each other are subjected to vibration or oscillation. Such movement destroys the protective lubricant covering each of the metallic surfaces and creates small metal particles which oxidize and become abrasive. Fretting corrosion may in time become severe enough to initiate cracks and metal fatigue, and cause subsequent failure of the part. Fretting corrosion is most likely to occur in those areas that experience the most vibration, the wings. The joint between the vertical stabilizer and each horizontal stabilizer, and each landing gear nacelle are areas that are vulnerable to fretting corrosion. The next corrosion type to be considered is known as stress corrosion cracking. Cracking caused by stress corrosion is the result of the combined action of corrosion and sustained tensile stress. Stress corrosion cracking is most likely to occur in high-strength aluminum alloys, magnesium alloys, corrosion-resistant steel, and high-strength steel alloys. Specific areas that are prone to stress corrosion cracking include the elevators on each horizontal stabilizer, aluminum alloy bell cranks with pressed-in taper pins, and exposed or overstressed tubing B-nuts. Corrosion fatigue is another type of corrosion attack which P-3 aircraft are vulnerable to. Corrosion fatigue is also the result of metal stress, but it is the result of cyclical or on-off metal stress rather than the sustained stress that is the cause of stress corrosion cracking. Corrosion fatigue sometimes causes shallow pits to form in the stressed area. Then if the attack is allowed to continue, sharp, deep pits may form, which develop into cracks, which can result in failure of the part. Areas on the P-3 that are prone to corrosion fatigue include trailing edges of movable flight control surfaces, bomb bay or trim tabs, wings and vertical stabilizer, and the flap tracks on the underside of the wings. The next corrosion type to be considered is known as filiform corrosion. Filiform corrosion attacks only surfaces that are coated with paint or some other organic substance. Filiform corrosion appears as countless tiny worm-like lines beneath the paint. The winding, twisting filaments, characteristic of filiform corrosion, thrive in areas where moisture saturates paint or other organic substances in environments of high humidity and high temperatures. Though filiform corrosion occurs frequently, little is known about what causes it. Watch for it on any painted surface. The last corrosion type we will consider in this program is known as microbiological-induced corrosion. Microbiological-induced corrosion is corrosive activity caused by microorganisms that enter the aircraft's fuel system from the air or through contaminants or moisture in fuel supplies. Such microorganisms, usually fungi, grow in the presence of moisture and attack the sealing material inside the fuel tanks, causing the tanks to leak. They also attack the tanks themselves. Microbiological corrosion clogs fuel lines, filters, and pumps, and causes erroneous readings of fuel quantity gauges. That concludes part 1 of this program, an overview of the fundamentals for identifying various types of corrosion. In part 2, we'll consider the fundamentals for treating corrosion.